Welcome everyone to this week's Autonomy Talks. This week is a great pleasure. Can you hear me? Yes. Science at Simon Fraser University in Barnaby, Canada. And there is the director of the Multi-Agent Robotic Systems Lab. He also holds a Canadian Institute for Advanced Research AI chair, and he's an AMII fellow. So something about Mo. Mo received his Bachelor of Science in Engineering Physics from the University of British Columbia in 2011, and then completed his PhD in Electrical Engineering and Computer Sciences at the University of California, Berkeley. Then he was for a while a postdoc at Stanford, and then he joined Simon Fraser. In general, his research interests are in multi-agent systems, safety-critical systems, human-robot interactions, control theory, and reinforcement learning. And today he's going to talk about some recent advances in control, reinforcement learning, and human-robot interactions. And those are his actual interests in his research. So I'm personally excited to hear more about it, and therefore I give you the stage, Mo. Go ahead.
Yeah, thanks a lot for the introduction. It's my pleasure to be here. So as was said in introduction, in our lab, we actually work on quite a number of topics, and today we'll be touching on just a few of them. So in general, we work on human-robot interactions, control, and machine learning. My PhD was actually primarily in control, and I've been looking at, with my lab, how control and machine learning can be combined together, and often in the area of human-robot interactions. So maybe another way to slice the work that we do in our lab is to look at the axis between control methods, or what I sometimes would call classical methods, and on one end, and on the other end, learning and sometimes called data-driven methods. So today I'll be just talking about three main areas, which I think are probably the most important. So first, in the pure control side, I'm going to be talking about computational challenges in what's called Hamilton-Jacobi reachability analysis. So I'll be introducing that a little bit later. In the middle, between control and learning, I'll be talking about how control and learning can be combined together to help improve data efficiency, generalizability, and also interpretability of learning. And finally, mostly in the learning side, I'll be talking about some recent work that we have done in human-robot interactions. Okay, so let's begin with the first part. So hopefully by covering a wide variety of topics, it will be interesting. At least part of the talk will be interesting to some people. Okay, so let me introduce Hamilton-Jacobi reachability analysis. So it's going to be a lot of material I'll be going through quickly, but hopefully the main ideas are pretty simple. So in reachability analysis, we model a dynamical system using an ODE, and we specify what we call the target set. So in the diagram on the right, the target set could represent something dangerous, and the system dynamics could describe something like a person riding a bike. So this is an overhead view. So let's say that the person wants to avoid this danger zone called the target set. So some more information. So we have the dynamic, state, control, and disturbance. And because we're going to be doing mathematical computations, we're going to be going back and forth between sets and also functions. And we're going to be representing sets using the sub-zero level set of functions. So that's shown mathematically here. Skipping a lot of details, we take this function as the initial condition of the Hamilton-Jacobi equation. After we solve the equation, we would obtain the reachable set. So that's depicted in blue. What that means is that if the bike wants to avoid the red region, it must actually start doing the avoidance before it enters the blue region. And that's because of the system dynamics. In physics, in physical terms, it just means that the bike has a limited turning radius, and also it has some momentum, so it takes some distance to stop. Okay, so solving this equation is actually just doing grid-based dynamic programming, and then we obtain this, what we call the value function. It actually sounds just like any value function that you heard of in control and in reinforcement learning, and where the sub-zero level set of the value function represents this reachable set. Okay, so I won't really go too much deeper, but doing all of this is actually equivalent to writing down the following definition of the value function, where we try to keep track of the minimum value. So we have to go from the inside to outside here. We keep track of the minimum value of L, which is the red, over time. And then we have a control that is trying to maximize or stay outside, and a disturbance that is trying to, we assume an adversarial disturbance that tries to bring us in, minimize, right? And then after some math, maybe a few pages, we get to one version of the Hamilton-Jacobi equation we see here. So I'm just gonna blow right past it. Don't worry about it. If you're interested, please contact me later, and we can spend a lot more time talking about this. Okay, so I just copy pasted a simpler version of the equation here. And I guess this is kind of a bit of repeating myself. The idea is that we formulate a control problem in terms of sets. We convert these sets into functions, and then we can do some computations on these functions to obtain another function, the value function, that represents the reachable set, which is what we want. And the nice thing of doing everything on a grid is that basic set operations such as union, intersection, and so on are actually equivalent to simple pointwise function operations. So for example, the pointwise maximum actually is the same thing as the intersection. Again, I'm not going to go too deep here. And this method of using finite difference to discretize the equation and then solving for the value function on a grid, it's numerically convergent. That means that as we have finer and finer discretization, we approach the exact solution. And because we're basically using dynamic programming here, the solution we get is globally optimal. Okay, so why do we care about this? Well, reachable sets can represent something very useful. For example, once you're inside a reachable set, in the previous illustration, danger is inevitable despite optimal control given the worst case disturbances. That means that if we want to avoid danger, we have to look a bit ahead. How much ahead is quantified by the reachable set. We can also have a goal reaching version of this, as well as any other variation which could model reach avoid situations, as well as constrained reach avoid. So we may want to reach some goal while avoiding some agents in an environment where we have constraints such as obstacles. Okay, so advantages, I kind of talked about that. We get globally optimal solutions and guarantees. We basically, because we're using dynamic programming, we get to handle disturbances and adversarial agents for free, basically. And we can handle nonlinear dynamics and sets of arbitrary shapes because everything is on a grid. But obviously, some of you probably noticed that the biggest disadvantage is the fact that we're doing grid-based dynamic programming. So this whole process is very expensive. So in the control side of things, in our lab, we have been looking at how to optimize grid-based dynamic programming. Intuitively, this should be possible because in grid-based dynamic programming, we basically have a bunch of nested loops. Kind of each nested for loop is basically taking care of one dimension of the state space, right? So this is actually a very simple algorithm, but it's just very expensive in high dimensions. So we have done some optimizations both in software and hardware. In software, we have developed this optimized DP toolbox. So it enables analysis of slightly higher dimensional systems, which allows us to more effectively combine these slightly higher dimensional base solutions with higher level logic that really scales up the dimensionality of the solution. So we'll be taking a look at one example of this right after this. We'll also briefly look at some hardware optimizations done via FPGAs, and this enables real-time applications. Okay, so to motivate the kind of the second point, which we're going to be looking at the multi-agent reach avoid game. And this problem has been studied quite a bit from many years ago all the way until today. It's still being actively studied. So The problem setup consists of M attackers and N defenders. It's kind of like a capture the flag game where the M attackers are trying to reach some target while avoiding capture by the N defenders. And there are some obstacles in the environment as well. So this is a very non-linear and non-convex problem. Because there are many agents, it's also very high dimensional, and the interactions are complex due to the competition and cooperation within and outside of the teams. So there are many solutions proposed for a game like this, and all of them need to make trade-offs among solution optimality, what kind of system dynamics and control policies can be handled, the number of agents that can be analyzed, as well as what kind of environments the agents are playing in. So we're gonna be using Hamilton-Jacobi reachability to solve this problem. But of course, I already said that Hamilton-Jacobi reachability is actually not very scalable to high-dimensional state spaces. If you have n attackers and n defenders, even if each of them are modeled by a single integrator, which has only 2 dimensions in their state space, we end up with 2 times n plus n dimensional joint state space. So one of the previous previous general solutions was obtained a while ago in 2015. It was just for the 2-player game, 1 versus 1 game, which had a 4-dimensional joint state space. So with a new software accelerated toolbox, we're able to bring in 1 more player, maybe potentially 2 more players, but we're still investigating the limits of this toolbox. Okay, so what we're going to do next is to formulate from the attacker's perspective how to use Hamilton-Jacobi reachability to solve this reach avoid game. So the procedure is pretty simple because a lot of the details of the game are actually abstracted away. So what we need to do is to define the target set, which is basically we want the attackers to arrive at the target or the defenders being stuck in the obstacle. We also define the avoid set, which just means that the attackers are captured or they get stuck in obstacle. So once we have defined these sets, we can turn them into functions, which then can be passed into the partial differential equation to be solved. And that will give us a the reachable set. In this case, it's actually called the reach avoid set. Okay, so just to go into a bit of detail, yeah, I think we do have some time. So let's just do the 1 versus 1 case, and then the 3-player game is basically the same thing. So the target set is just a set of joint states from which the attackers have already arrived. So sorry about the mistake here. So the target set represents a set of states in which the attackers have already arrived. So that means that they've already won. So this is the set of joint states such that the attacker is in the target and is not captured by the defender, or the defender gets stuck in the obstacle. And then next we can define the avoid set, which just means that the attacker gets captured or goes into the obstacle. So once we have defined these sets, we turn them into functions, and then we can kind of use the PDE as a black box to give us what's called the reach avoid set. We're going to be considering the infinite time horizon game in this case. Okay, so now the 3-player game is very similar. We're going to be considering 2 attackers and 1 defender. So I'm just going to be talking about the English description. So the target set is defined by either attacker getting into the target set and not getting captured by the defender. So here we're considering 1 defender trying to defend against both attackers. So if any of the attackers reach the target set, then the attackers win. Again, you can easily transcribe this into sets, and then the sets can become functions that we can kind of pass into the PDE. Okay, similarly for the avoid sets, we basically say that the attackers lose if one of the attackers is captured by the defender or gets stuck in the obstacle, and at the same time, the other attacker is not inside the 1 versus 1 reach avoid set, right? So the other attacker is not in a position to win the game 1 versus 1 versus the defender. And again, we can write the set down. They look complicated, but we can easily convert them into functions. And all of these unions and intersections, they're just pointwise operations on a grid. So all of these actually, they turn out to be pretty easy to write down. So the result we get is called a reach avoid 2. I mentioned that these games are kind of being played out in a 4-dimensional joint state space, in this case, on the left, and a 6-dimensional joint state space on the right, with 3 players. So to visualize these sets, we basically fix one of the players and then look at the 2-dimensional slice of the reach avoid tubes. So here, so just as one example, maybe we won't be looking at all of these in the interest of time, but how about the middle one? Let's do the middle one. In a 2-versus-1 reach avoid game, we're going to be fixing the position of one of the attackers and one of the defenders. So they're shown in green. So given this fixed position, we can see that the other attacker must be inside this purple region in order to win the game for the attacking team. And if the attacker is outside of this region, then that means that the attacking team would lose. So although we're showing a 2-dimensional slice, all of the possible combinations of initial conditions of the 3 players are already kind of solved by solving the problem in the 6-dimensional joint state space. Okay, so that basically gives us a solution to a kind of a small base problem. Previously, without the new toolbox, we were only able to solve this 2-player game, but now we're able to solve the 3-player game, which gives us a lot more room to try to use higher level logic to tie together these solutions to the base problem. And the higher level logic, in this case, is given by a mixed integer program. So here, the idea is that we're going to be imagine that you're the defending team and you would like to try to capture as many attackers as you can. So we can kind of easily write down this mixed integer program where we're maximizing the number of defenders, the number of attackers that can be guaranteed to be captured by the defenders. So that's kind of, so EIJ is a binary variable, which is 1 if attacker I can be guaranteed to be captured by defender J. Okay, so while the first constraint is pretty trivial, the second constraint is basically saying that we're bound by our computation. One defender could be assigned to at most 2 attackers, assuming that the 2 attackers can indeed be stopped by the single defender. The third constraint is kind of like a defender's resource constraint. We're just saying that if one of the attackers is already being taken care of by a defender, then we don't really need to we don't need to assign another defender to capture this attacker. Okay, and then the next constraint is basically saying that we should only assign defenders to attackers if the defender is guaranteed to win either the 1-versus-1 game in this case, or in the last constraint, the 2-versus-1 game. So by formulating this pretty simple mixed integer program and combining it with the optimal solutions to the base problem, we can actually get some pretty interesting behaviors when we actually play out the game. So here I'm showing a 6 attackers versus 2 defender game. And you can kind of see 4 time snapshots of the game being played out. In blue, we have the 2 defenders, and in red, we have the 6 attackers. And the green lines are basically showing, in this case, this defender is actually assigned to these 2 attackers. And these assignments can actually be computed in real time because this mixed integer program is actually very small and therefore very quick to solve. Over time, some of these agents, some of these attackers are actually captured, shown by the cross. And when that happens, the defenders can be assigned to another attacker. And as the game played out, the 2 defenders work together and capture all of the 6 attackers. Of course, in this case, we set up the problem such that the defenders can indeed be captured. But in general, we actually maximize the number of attackers that can be captured. And we actually do this assignment in real time. Okay, in another game with 8 attackers versus 4 defenders, and you can also see that we have some kind of interesting behavior with these real-time assignments of defenders to attackers. So I won't be going too much in the detail here. Okay, so that was basically the whole discussion about the reach avoid games. Is the main message here is that by increasing the dimensionality of the base problem that we can solve, and then combining that with higher level logic provided by the mixed integer program, we're able to kind of analyze some very complex games involving cooperation and adversarial behavior, and while maintaining guarantees on being able to capture the attackers. So that was for the software optimizations of dynamic programming. And here I would like to just in one slide show you some results that we also got with hardware acceleration. So this time we're actually looking at a completely different problem. The point here is actually that to show that we can respond to changing environments in real time in this collision avoidance demo. So we're going to be starting with the left. Here we have a student actually driving this remote control car, and the student who is driving, he's actually not on camera. He's actually trying to drive the car into these obstacles. And at the same time, another student is trying to change the environment in real time to try to place new obstacles in front of this car. So the car is actually receiving commands from an FPGA, which is computing the reachable sets for avoiding these obstacles in real time. And we can see that the car is able to, through the real-time computations, always able to avoid collisions in the changing environment. And on the right, we just see a run of a different experiment. So this time, instead of a sudden obstacle change, we have a student trying to move some obstacles around. Okay, so that was basically some ways that we've been addressing the computational challenges in reachability analysis. So next, let's take a look at how a combination of control and learning can make learning more data efficient, generalizable, and interpretable. Mostly, I'm going to be focusing on the interpretable part, and I'm going to motivate it through linear systems. So linear models are very good for control because I'll just use the LQR as an example, right? So the LQR problem, I think most of you probably are familiar. We're minimizing a quadratic cost subject to linear dynamic constraints. So this problem actually has a very simple solution. It's nearly closed form. The solution turns out to be linear feedback, where the feedback matrix is given by this expression here, where one of the matrices solves the discrete algebraic Riccati equation. So mostly this is very quick to compute. It's almost analytic and is easy to interpret and implement. So probably many of you may even have done a lab where you have stabilized something like the cart pole system around an upright position using LQR. So unfortunately, most of the systems, as you know, are nonlinear. And there's some, but perhaps fortunately, there's a Koopman theory, which basically tells us that there exists for some systems a potentially infinite dimensional mapping of the states, such that in the mapped coordinates, we actually have a linear system, right? So in math notation, it could be the case that if you kind of apply some function phi to x, the resulting state space phi of x could actually be linear. Of course, in general, the phi function is very difficult to find, and this phi could also be infinite dimensional. So this has been known for a while. there's a really good set of lectures on YouTube by Steve Runton. If you would like to get more insight and a better introduction to the Kuban operator framework, please take a look at his lectures. So here I'm just going to be skipping through most of the basics on Kuban theory. Okay, so in recent years, because of the rise of data-driven approaches, one of the approaches people have been studying are to first use data to train, to basically obtain this phi function, so that under the mapping phi, the system becomes approximately linear. And after this latent model identification step, we can then design a controller to basically do linear system control. Okay, so I think for some very simple systems, this what I'm calling the two-stage approach, which is model identification first. So again, this involves finding a globally linear system using a data-driven method. Once we find this globally linear system, we can then try to design a controller. So that's why it's two stages. So some challenges of this two-stage approach is that sometimes we're actually not able to find a good linear model of the system. And therefore, it can result in poor control performance. Other times, even when we're able to find a good linear model, we still have to tune the controller. So for example, if we're using an LQR controller, if we tune the controller very well, then we could achieve pretty good performance. But because the Q and R matrices, they can become not very interpretable in the latent state, right? So after we map the states, it can be unclear which of the latent states are the most important. And therefore, it can be very difficult, for example, to assign the right Q matrix in the LQR problem. Right? So with a poorly tuned LQR controller, we can have some less than desirable performance. So what we investigated in this area is actually to propose a one-stage approach where we combine kind of where we're using reinforcement learning to try to optimize the control performance. And we're not just optimizing, we're kind of doing the optimization of the controller as well as the model identification all at the same time. So from a control perspective, you can think of combining these two steps into one. So using data that we obtain during exploration of the environment in the RL process to update everything at once. From a RL perspective, you can think of what we're doing as doing RL with representation learning, where the representation is forced to be a linear system. Okay, in particular for the encoder. So the encoder isn't just another word for the phi function. We're encoding the state into the latent state. So for the encoder, we're using a contrastive encoder. So hopefully that will give us a linear system, and the linear system can then be we can then use an LQR controller to control the linear system. So it turns out that all of this is differentiable, even the LQR part. Okay, so I think I'll probably skip the math here, but I think if you're familiar with the contrastive loss, this is basically pretty typical. The second loss that we're using is basically the prediction loss. So we're basically saying that if we compare the next latent state to what our dynamic predicts, that error should be low. In here, we're basically saying the LQR controller should perform well for the task. Okay, so in the interest of time, I'm going to be skipping this slide. Okay. So let's first take a look at results for model identification. So first, we used a very simple example to see whether this one-stage approach is able to give us a pretty good globally linear system. So this is a 4D cart pole system. So here you can see basically the model error is decreasing over time as we train the encoder. And on the right, we're showing a projection of the predicted next state and the actual ground truth next state. So we can kind of see that our model identification is not perfect, but for the most part, it's doing a pretty good job. Our linear dynamics are doing a pretty good job of predicting the next state. We also applied our method to much higher dimensional systems, such as the 18-dimensional cheetah system, half cheetah. So this time we can see that the model is slightly worse, but we do see a general shape. We do see that the predicted and the ground truth sort of follow the same pattern. Again, it's not perfect, but we're getting some kind of good representation in the latent state. So, okay, so we compared our method we compared our one-stage approach to the two-stage approach that we saw earlier, and we found that we are more resilient to modeling error. So despite having some modeling error, we're still able to perform much better compared to the two-stage approach. And another observation that we made was that now the one-stage approach is much more convenient because we don't necessarily need to try to find a good Q function to tune the cost. And again, we achieve much better results compared to the two-stage approach. So I'm going through this kind of quickly, but just going to be talking about the takeaways. So the one-stage approach, the main takeaway is that better resilience to modeling error. Of course, this is kind of expected just because we're doing reinforcement learning on the very outside, right? So even if our model is slightly wrong, reinforcement learning is still able to optimize getting good, performing the task well. Okay, and obviously, since the Q is part of the variables that we're optimizing, so we automatically get some Q matrix that leads to good performance. So we also compared our results to traditional model-based RL, where we're not enforcing the model to be linear. We can see that we're outperforming one of the popular methods, Planet, and we have comparable performance and data efficiency with Dreamer version 2 in these three tasks. So we have looked at the 4D and 18-dimensional tasks, but we also looked at another task involving the cart pole, but this time with pixel observation. So of course, one of the benefits of forcing a linear model is that we have better. So, okay, it looks like I removed that slide in the interest of time, but we also have some results on looking at the controllability of the linear system, and we found that we also looked at the poles and zeros of our learned system, and we found that they match the actual poles and zeros of the original nonlinear system. And the controllability characteristics of the learned linear system also resembled that of the original nonlinear system. So on top of the comparable performance to state-of-the-art model-based RL, we also have better interpretability. Okay, it turned out that our method could also be transferred without any additional training to a real robot. So here we have a pretty simple task of taking as input 2D LiDAR and odometry to a policy network, which outputs linear and angular velocities of this turtle bot. So using our one-stage approach and using RL, we're able to actually train everything in simulation and then deploy our policy on a real robot. So again, I would say maybe from an RL perspective, nothing groundbreaking here. The main point here is that we're able to generalize fairly well. We're able to have similar performance to some of the model-based RL methods. But in addition to all of that, we have interpretability. Okay, so I'd like to just quickly go over, sorry, actually, let me skip to over here, where I'm gonna kind of switch gears a little bit to, again, reinforce the usefulness of combining control and learning to provide generalizability. So in this task, we have a visual navigation task where a robot is using just an RGB camera to go through narrow doorways. So this is a pretty difficult task. We have some shiny floors, which makes visual SLAM difficult. And previous methods on visual navigation could not really complete the task adequately. So here the main challenge was that because of neural network errors, if we generate training, if we try to force the robot to go through this narrow doorway, a lot of times we saw that the robot would make some mistakes and it would kind of go to the side of the door and therefore colliding. So here what we did was we generated a lot of synthetic data using Hamilton-Jacobi reachability, and we use disturbances to kind of account for these neural network errors. So as a result, our train policy was able to robustly go through the narrow doorway to reach its destination. And again, we're able to deploy this on a real robot without any additional training in the real world. So this was a paper back in 2020 in L4DC. Okay, so in the remaining time, I'm going to be briefly talking about human-robot interactions. So part of it is actually human motion prediction. So there are several types of human motion prediction. One is more focused on a position. So here, perhaps a lot more used in robotics, where we predict the trajectory of the human over time. And usually if you do this, the purpose is to plan a path for the robot that avoids the human's trajectory. In computer graphics and computer vision, it's actually very common to do pose prediction. This just means that we're predicting the joint positions, so the arms, legs, predicting the skeleton of the human. So for both cases, there could be a probabilistic predictions or deterministic predictions. And recently, we have been looking at combining the pose and trajectory predictions together. And we have done both the probabilistic and deterministic case. Okay, so for the probabilistic predictions, this can be useful in robotics because humans are unpredictable. So sometimes it's actually pretty useful to account for multiple possibilities. In the deterministic case, this is more beneficial for a faster runtime, especially if we're using not so fast hardware on a robot. So it turns out that prior works on combining pose and trajectory predictions is pretty limited. Mostly the vision community is focusing mostly on the pose predictions relative to the hip. And they don't really consider the kind of the absolute movement of the center of mass of the human, which is very important in robotics. So this is kind of the gap that we're trying to address with some of our recent work in ICRA. So we were predicting both the 3D pose of the human as well as the human absolute trajectory. So briefly, I'm going to be talking about DMM-GAN, which basically takes as input the motion of the human. So motion includes the trajectory shown in the dotted black curve here, as well as the pose, 3D pose of the person. And then we're going to be passing into our trained model, and then it's going to be predicting multiple possible outputs of the human. So we're borrowing some recently popular architecture of the transformer. So as input, we take the 3D pose and the 3D hip trajectory, and then we pass it into a 3D pose module, which includes a transformer encoder and a generator consisting of GRUs. Actually, we have a new version that also uses transformers for this part as well. But for this paper, we were using GRUs, and these output multiple future movements of the human. In order to make sure that these are plausible and accurate, we're using several different loss functions. On the bottom here, we're doing the same thing with the hip movement predictions. So we have several loss functions. The similarity loss, which should be actually called a dissimilarity loss, because we're trying to promote all of these different outputs to be different. So we have a diverse set of predictions. You have a teacher forcing loss, which is pretty common when we do sequential predictions. And we also have a joint loss, which basically is saying that human joints tend to be of certain lengths. And if we are predicting the human arm to be too short, for example, then well, that gets a high penalty. And lastly, we have a best loss, which basically looks at the prediction that is the closest to ground truth, and then makes that prediction even closer to the ground truth. Okay, so on top of all four losses, we also have a discriminator module, which basically makes sure that all of these predictions that we make are similar to the distribution of the data. The data we used to train our model was the human 3.6M data set. Okay, so that was a bit fast, but the idea is that I think the main takeaways here are that we're able to perform prediction of both the pose as well as the absolute hip trajectory. And in addition, we'll see later on that having a prediction of the 3D body pose is actually very helpful for predicting the absolute movement of the hip. And this kind of makes sense because when we look at other people walk around, for example, their body postures, their body language is actually pretty helpful for us to predict which way they're going. Okay, so some quantitative results. So let me just go to the slide. So for all of these metrics, the first metric is the diversity metric. The higher, the better. So we have much higher. We have higher diversity compared to the state of the art. So again, as I mentioned, it turned out that there's not too much work on this area, because most of the vision community has been focusing more on predicting the body pose relative to the hip. The other four metrics are on the accuracy of our prediction. So in the interest of time, I won't be going over them in detail, but they're on this slide. So again, we slightly outperformed the state of the art. We also have some quantitative results, which basically look at these are ablation studies for some parts of our model. So first, we adapted DLO, which is a previous method, the previous state of the art, for only predicting the body pose, not the hip. It turns out that a trivial modification to that model did not give us a good performance for our task of predicting both the pose as well as the absolute movement of the hip. Next, we took out the similarity loss, which promoted the diversity. Once we take out this loss, we can see that we have much worse diversity. And next, we looked at predicting the hip motion without using information from the body pose, and we found that the accuracy goes down. So the accuracy goes down. So that's the bottom row here. It's actually higher compared to our method. So this is basically saying that the body pose is indeed useful information for predicting the motion of the person. Okay, so in the interest of time, I'm going to be skipping over the details of this kind of the qualitative predictions. So I guess as I talk for a little bit, you can kind of just look at some of these predictions. So the top row is ours. To be honest, it's a bit hard to see what the difference is through these qualitative results. Mostly the quantitative results kind of tell the story. So I think maybe I'll move on to something which I find to be a bit more interesting from a robotics perspective. So we applied these predictions on the follow ahead task. So the idea is to have the robot predict the motion of the human and then try to stay in front of the human. So this is actually a very difficult task because you can kind of see that this whole joint system is pretty unstable. And if the robot cannot accurately predict the human's motion, then it cannot really perform this task very well. So jumping right to the results, we can kind of see, let's look at the left top first. So the person is walking in an S shape, and you can kind of see that the robot somehow predicts the human motion and takes a shortcut to get in front. And then is able to mostly stay in front of a person despite starting behind the person. And on the left bottom, we have a U-turn scenario where the robot is actually, again, predicting that the human will turn around and taking a shortcut to stay in front of a person. So these motions were actually, they were trained in simulation. Sorry, actually, these were not, we had some other work that was using RL, as you will see later on, but this work is purely using the predictions. So it's predicting the human motion and then simply driving the robot in front of the human. The interesting thing about predicting the body pose is that we can now have the robot understand what it means to have a human starting from sitting down and then standing up. So in this experiment, we had the human sitting down first. When the robot predicts that the person is about to stand up, it quickly travels in front of the person. As the person moves forward, the robot stays ahead. And when the person stops and then moves backwards, the robot is able to follow while at the same time always stays in front of the person. You can kind of imagine this could be something like an autonomous luggage bag, for example, right? We would like to have our luggage in front of us. It could also be an autonomous shopping cart where the shopping cart is kind of always being in front of us. Okay, we can also do other types of following, for example, following beside, right? So the robot here is now always to the left of the person. So it's trying to be on the left side of the person. And as the person makes a U-turn, because the robot is able to predict the motion, it doesn't, it simply turns in place to stay in the right position. So we have extended this work by adding reinforcement learning in order to handle situations involving obstacles as well as occlusions. So here, the robot can learn to avoid colliding with obstacles as well as avoiding losing line of sight of the human. So here we have combined Monte Carlo tree search with reinforcement learning, where this combination is used to predict a high-level waypoint for the robot to move towards, and the robot uses a simple low-level controller to move to these waypoints. In order to perform the Monte Carlo tree search, we basically need a model of a human. We need a model of the robot movement, as well as a model of how the human might move. Right? So you can imagine that the whole thing about predicting human motion, that could be a good model of human movement. And of course, robot movement, we have dynamic models of these simple robots. So by using Monte Carlo tree search, should be MCTS, sorry about that, we're able to explicitly account for potential human reactions to robot actions. So this is something that I find understudied. A lot of times in human-robot interaction, we simply have the robot react to the human, but here we account for potential human reactions to the robot as well. So just without going into too much detail, we're going to look at one example where the human is moving in an S shape. Over here, you can see an obstacle that the robot is able to avoid. So again, this axis here is the robot. The red arrow is the robot's high-level command. And this black and green arrow is the human. So maybe we can look over here as well. So as the human turns around, in this case, the robot squeezes between the obstacle and the human in order to avoid the obstacle. Okay, so I think that concludes my talk. So today we kind of just looked at one slice of the work that we're doing in the Mars lab at SFU. And we're kind of looking at the spectrum of control and learning, and we looked at some pure control methods, some combination of methods involving the combination of control and learning, as well as some mostly learning-based methods for human-robot interactions. I would like to thank the members of my lab for their excellent work, and I'd be happy to take any questions. Thanks so much for your attention.
Thank you very much, Mo, for the great talk. A lot of cool projects. Let's open the stage for questions. You can either ask in the chat and I can read for you, or you can directly unmute yourself and ask. So who wants to go first? Okay, maybe I can be the icebreaker. So you presented a lot of cool applications, and one question that came to mind is especially regarding the first part of the talk, so this more classical methods, was how robust are those methods to slight changes of the cost functions? What I mean is, you are showing very cool results, but does it also mean that one has to design the cost functions very carefully? Or can you start from first principles, I don't know, prioritizing some things over others, and this works in most scenarios you encountered?
Yeah, so that's a great question. So actually that's so because we need to start with some, in this case, I'll just go back to the reach avoid games. If we start with some target set and some avoid sets, we kind of define a static environment, right? So given some static environment, so let me back up a little bit. When you say cost functions in reachability, it really means these target sets and avoid sets, right? Because all of them will become kind of functional representations of these sets, which are the cost to our control problem. So the main, I guess, one of the disadvantages that didn't really get to touch on is that we can only solve these problems in static environments. So we have to define a particular goal, a particular constraint, and if we change them, we have to solve the problem again. There have been some recent work, not really from our lab, but some recent work looking at warm starting the solutions to these to this PDE, right? So for example, Sylvia Herbert from UCSD, she was looking at what happens when you change the problem slightly. Can you initialize the solution to be kind of a solution to a nearby problem in some sense? And then would that lead to a much faster solution? So in some cases, yes, but in some cases, no. So yeah, so the solution definitely does change depending on the cost function.
Okay, I see. But so do you think that the fact that you are relying on this chain of static solutions, does it somehow restrict the kind of applications you can look at the moment? Because I mean, you're saying, in some sense, you were showing some things that were pretty complex, right? For instance, I refer to the video in which you were changing the obstacle position very quickly. And
right.
So it seems to already deal pretty well with the dynamic environments.
Okay, yeah, that's a great question. So I think it's a great opportunity for me to clarify something. So the environment is static, right? But what exactly the environment is actually the joint state space of all of the agents, right? So things like the obstacle, the goal, those are static, but the agents and their interactions, that's not really static. But so we can definitely allow for these agents which are always moving around all the time, because they're all moving around in a joint state space, right? So as they move around, we can always come up with a controller in real time to kind of adjust to the situation. So now what happens when the environment is actually changing, which is the case in these two videos. Well, in this case, we got around that, I guess, in a brute force way. We actually run the computations on an FPGA so that they can actually run in real time. So in this case, we got the computation speed. So that means solving the partial differential equation. We're able to do that within 0.2 seconds. So every 0.2 seconds, we update the environment, we resolve the equation, and then basically we recompute the reachable set, right? And because we're able to do that, the car is able to, in real time, respond to the changing environment.
Okay, I see. So this makes a lot of sense. And maybe I assume that this could become challenging if you want to do it at high speed in scenarios where things are changing very quickly, like, I don't know, a road with an autonomous vehicle or this kind of things.
Right.
Okay.
So a lot of times it becomes a question of how you model the problem, right? So if you have another agent, we could model them as literally another agent in this case by augmenting the state space to include the states of the other agent. In that case, we can always account for any behavior of the other agent. But if you're changing static obstacles and things like that, then that's kind of a different way to formulate the problem, right? So there are some trade-offs. If you want to account for all possibilities, what we do is usually augmenting the state space, which I guess you could argue is a kind of a brute force way of doing it. But if we do that, we could definitely account for these any possible change in the environment.
Yes. Thank you very much. Is there any other question? I guess you gave very good explanations then.
If you have more questions, I think I went by really fast. My talk was a bit longer than I expected. Yeah, but if you, I guess the talk is recorded. If you ever have any questions, please feel free to email me. Let me just pull up my email. Yeah, so here's my email. So please feel free to reach out.
Yeah, now we see it. Yeah, and thank you. So I take maybe the occasion to thank you, Mo, for the great talk, and thank you all for participating, and see you all next week for the next talk. And Mo, I will follow up with the video once I've been edited.
Okay, yeah, thanks so much for inviting me. It was my pleasure to be here.
And enjoy your day in Canada.
Yeah, thank you.
Thank you. Bye-bye.
Bye.